Okay, so good afternoon, everyone. Thank you so much for coming to this tutorial session. My name is Theja, and I have Son and Tommy with me. So today we'll go over training-free alignment of LLMs. So I wanted to quickly give introduction to ourselves. I'll do mine and later them. As I said, my name is Theja, and I'm an associate professor at University of Illinois, Chicago. I work on topics in optimization and machine learning a few years ago, and now more applied machine learning and LLM-based systems.
Yeah, and my name is Sun. I'm also work on LLMs based system, especially designing optimization in training-free environment.
My name is Tommy. I'm actually from the biostat department, but I work with Professor Theja on LLMs applications and specialize in studying prompt engineering.
Okay, so as Son and Tommy will take over, just a couple of, I guess, housekeeping items. So please feel free to interrupt and ask questions. It's a heterogeneous audience, so maybe some of you are already experts in something and some of you are new to topics. So please feel free to interrupt because it's a small gathering here. Thank you.
All right, thank you, Teja.
Right, hello everyone. So today we're gonna go over training-free alignment of language models. So it's gonna be 3 hours, approximately hands-on tutorial. All right, so regarding to the table of contents, so first of all, we're gonna go over some motivation regarding training-free alignment. Then we're gonna go to 3 umbrellas. One is prompt engineering. Second one is guided decoding. And the third one is response engineering. And then lastly, we're gonna have question and answer as well as wrap up. All right. So as you may also experience, large language models becoming more and more powerful, right? So from a couple of years ago, is only be able to do question answer, right? But forward to now, it start getting more powerful. So right now it can also do train a classifier, or it can implement complex protocol for some really complex system, right? So however, they don't always behave as expected, right? As you may know. So how many of you here have experience with language models, for example, ChatGPTs, and then sometimes is starting to derail, going to a different way than what you expected? Raise your hand. Okay, almost everyone. That's me too. Right. So, all right. So, more capable isn't equal to more reliable, right? So, because LLMs is a very stochastic system, so it can give wrong information in a very confident way, right? So it can give you very hallucinated citations. It can give you biased decisions as well. If you ask it to give a decision for on something, right? So on high stake setting, it's very dangerous. And as it's getting more and more autonomous, so it can get even more dangerous. It can be able to get deceptive and maybe disobey and then cause harm. All right. So here are some cases of earlier failures, right? So for example, there's a famous case on Air Canada chatbot invented a non-existing policy, right? So it's just when they went to court, it's just a couple of $100 refund to the customer, right? So there's like also a ChatGPT lawyer hallucinated 6 court cases, or Amazon recruiting AI penalized women's CVs. So also Google Gemini, when they launched the Gemini application, in the live event on stage, it gives wrong answers, right? However, these are very low consequences. maybe a couple $100, maybe a couple $1,000, right? But not really, catastrophic, I guess. All right. So recent failures, when these systems incorporated into agentic system, right, is getting more and more autonomy, their consequences may be more catastrophic. For example, O1 and O3 models hide their reasoning, right? And then it's denied that they hiding the actions. So for Replit coding agent, it deleted the production database, then lie about it. And then recently, anyone have experience with OpenClaw? Right? No? You heard about that? Yeah, so recently you heard about OpenClaw and made a alignment director. So it started to delete her inbox and then just ignore the stop command. So it's become more and more, I guess, catastrophic, right? All right. So from the examples above, I hope that you understand the importance of alignment, right? So making AI behave as what we want it to behave. So it's powerful, but it doesn't equal reliability. So the outputs can be harmful, deceptive, and also very unhelpful, right? Can just be simply as unhelpful. You don't want unhelpful assistant as well, right? So the point or the motivation of alignment is to make the model behavior consistently match with human intent, values, and expectations. For example, it can't just be as easy as correctness in math, or factual accuracy, or appropriate tone, or don't lie to me, don't delete my database, right? So how do we do this, right? How do we measure alignment? So just like you are taking an exam or a test, we're gonna give an AI a test or a benchmark or a golden data set with inputs and desired outputs. And what we wanna do is we wanna evaluate the AI performance against the evaluation matrix. So evaluation matrix here is very general. It's about alignment. Whatever is not coming from expectation, we can call it unaligned, right? For example, example 1 here, right? So what is 2 plus 2? The desired output is a factual output is 4. However, the AI, as you know, ChatGPT just a couple years ago cannot solve math problem very well. They may give you 5. So that's become like unaligned answer, right? And our job is to be able to steer that output to make it align. For example, go back to 4. So the score here or improvement here from unaligned, which is a 0, now is aligned, it's become a 1. Then we count it as a success case, right? And also for safety as well, right? In safety, it's open-ended. We don't have a calculator or we don't have a verifiable result way to check it, right? For example, when somebody asks it, how do I pick a log? So the desired output is going to be what? Refusal, right? I don't want to answer this question, or it's unethical for me to answer this question. But an unaligned AI gonna give the user step-by-step instructions. And then that not good, right? Because that's a very dangerous prompt. So the way to align it is to steer the output from step-by-step instructions to make a refusal answer. All right, so the score here or improvement here from 0.1 for very dangerous to 0.9, for example, for aligned result, right? So how many types or how many ways that we can, right now that we have to align AI, right? So as of right now, there are 2 main types. One is training based, and the other one is training free. Okay, so training based is a traditional way of aligning AI. So it's require you to train the model or fine-tune the model, modifying the weights. For example, you can use reinforcement learning. You can use supervised learning. You can use preference learning, or you can use steering vectors, right? And for training free, which is what we are focusing on today, we are focusing on steering behavior at inference time without modifying or without retraining or fine-tuning the weights, right? So there are three types, main types within training free. One is pre-generation. What can you do pre-generation? What you can do is you can steer the prompt, right? You can do prompt engineering. And then what can you do in generation? When it's generating, what can you do? You can do guided decoding. And what can you do after that? So post-generation, you can do response engineering. And then today we're gonna go over those. Okay, and why training free? Okay, I hope you know that in order to train or fine-tune AI as of today, it's very costly. It's require you to have label data, high compute. So you need to have multiple GPUs. Yeah, it's gonna require you to deploy in cycles, right? And it's very slow. And it's hard to adapt quickly because the model is huge. Okay. And then that's why training free is very practical, right? Because it's require no training, low output costs, fast iteration cycles, and then easy to implement. Go ahead.
And given that it's more training based, it's possible that you have like a better effect at the
Excuse me, I can't hear you.
The question is there a limit to, I guess, one method?
The alignment is training based versus training free.
Okay, so how effective is each of them? All right. So yeah, so it depends on the task, right? So for easy tasks, you can just use training free very easily. Okay, and then it doesn't make sense to, for example, if you can do align it with a prompt engineering using prompt engineering, right? So if you can do that, why do you need to fine tune it, right? Because fine tuning is costly, right?
The training free is kind of like it's not guaranteed.
There are limits to how much you can align. Maybe there's a con slide.
Okay. Okay. The con to training free, is that what you're asking? Okay. Okay. Sorry about that. Yeah, I am unaligned right now with it. All right. So yeah. So So the trade-off of training free is longer inference time for sure, right? So because you are trying to fixing it at inference time. So it's require you to have longer inference time. It's require you to have higher query cost, right? You have to do multiple API calls to OpenAI or something. Okay, it's not persistent across intersection, right? You have to apply that again and again. For training way, right? The training base, you do it during training, and then it persists when you do inference. Okay, and then it's weaker than fine tuning for a very complex task. Okay, that's the trade-off. Okay, so training free methods shift costs from training time to inference time. There are some pros and cons, right? So go ahead.
I just want to add, so your question is a very central question, right? So how much can you push the alignment levels by just doing post-training methods versus, compared to, let's say, fine-tuning based methods? I don't think there's a generic answer, but that is an important boundary. So what's the boundary? How much can you align based on tricks with the inference time tricks? versus what you can do during training. So that boundary is, I think, case by case dependent, but that's a central point.
All right. Thank you, Theja. Thank you for your question. Go ahead.
The alignment phase or the worst case scenario. So although it is easy to do, but it's also easy to reverse engineer, right?
Okay, so the question is, can we guarantee that you have aligned when you've already deployed the model?
That's
How do you know that you're not going, how do you know that you're not, you're off when an actual user uses your system?
okay. So that's the reason why we are measuring it via test, right? That's the as of right now, it's the best way that we can do, or we can monitor it live as well, right? So when something is wrong, you can just fall back on a safe system. That's also what we're gonna do in an exercise here. Okay. All right. So when to use training-free approaches, right? Of course, it's not going to be applied for every cases, but when you have limited upfront resources, right? You don't have enough GPUs or you don't have enough computes to actually train your data. Yeah. Okay.
With logic post training, we also want to do the budget slash the like an extra layer.
Yeah.
Yeah, so your comment is that there's an extra layer.
Right?
Yeah, that's true.
That's
Like make it like one or the other. Like I feel like embracing both.
Yes.
That is
so
correct.
You can do both.
Yes,
The
and
right
Mhm.
direction of how people are thinking. So it's basically, you could think of defensive depth, like you can do training, alignment, fine tune and align, but then also do post training align. But sometimes most organizations will not even have the know-how or the computer skills to do fine tuning. Maybe some of you have already done fine tuning, then perhaps like how complex it is, especially if you're spinning over from single GPU to multiple GPU. So yeah, but I agree with you.
Yeah. Thank you for the question. Thank you, Teja. And yeah, usually the combined approach should be the one that is the best. But if you combine it, the cost also adds up, right? So one way of combining should be you can use training-free approaches at first to collect data, and then you can refeed that into your training-based alignment to make it persistent, right? That's just one way to do so. All right. So, and also when you have rapid iteration, right? So you want to prototype something very quickly, you can use training-free approach to demonstrate your alignment effort. And then when you have task-specific control, right? You have one language model, you want to deploy it to multiple people. One of them one legal tone, and then one of them some other tone. Do you want to split the model and then train two separate models, each for each user? No, right? All right. So, and then the last one is when you have frequent policy updates. So when when the update is very, very frequent and it changes rapidly, you want to also do it rapidly as well. Change the policy rapidly as well, right? You don't want to wait for like half an hour or days or a couple of days to update the model, right? So, and then for the rest of today, we're going to go over prompt engineering, lecture and hands-on, guided decoding, lecture and hands-on, also response engineering, lecture and hands-on, right? And now I'll pass over to Tommy for prompt engineering.
Thank you. So hello everyone. Thank you again for coming to our tutorial section for the training free alignment. My name is Cheng, and I'll be presenting this part on prompt engineering for alignment. So going back to the training free alignment framework, prompt engineering is in the pre-generation stage. Sorry. So prompt engineering is in the pre-generation stage where we will adjust the prompt or massage the prompt before we throw it into the LLMs to give response. So this is a overview of the parts that I'm going to present today. I'll first introduce the system prompt and instruction design, followed by some strategies that we can do prompt engineering, which is a few shot prompting and the chain of thought reasoning prompting. Followed by that, I will also introduce a automatic prompt engineering pipeline. And specifically for today's tutorial, we are focusing on using DSPy, which is very flexible libraries that you can create the prompts without manually crafting it. And we'll end this part of section with a hands-on tutorial showing a Python notebook demonstration. So as mentioned before, why do we want to do prompt engineering for alignment? So as Son mentioned before, doing prompt engineering is very low cost compared to spending a lot of computational costs or money to actually retrain the model or fine-tune the model. And also for some like not expertise or like experts in AI, where they don't know about the structure of transformers, they can just do prompt engineering to do alignment because all they need to do is just type and manually adjust the prompt. So as mentioned before, there are three core strategies that we're going to look at today. The first one is the single shot, few shot, and a chain of thought prompt engineering approach. So let's start with system prompts. So we can think of system prompts as sort of like a guidebook for LLMs. And adapting the Google Prompt Guide 101 guideline, a good system prompt should have 4 elements. The first one is the persona, which we will give the LLM a role or a scope of authority. The second one is the task, which we will tell the LLM what to do and what not to do for the alignments that we want the LLM to behave. And the next one is the context, which we can provide some background information or relevant data for the LLMs. And lastly, we also wanted to define some format, which would guide the LLM to output the structures that we wanted from the model. And let's take a look at a zero-shot prompting example. Here, this prompt follows closely to the structure that we described, where we defined the persona as a math tutor, and the task is to solve the problem. And we're providing background information that this is a basic algebraic question. And lastly, we are restricting the LLM to produce the answer in a numerical answer only, without any other units, variables, or steps. So obviously, this is a very good and straightforward approach. And I believe like most people, when they first use LLM, is using the same strategy, just providing an instructions. But however, this approach actually falls short in some complex tasks or some ambiguous edge cases. Which brings us to the next strategy, few shot prompting. So to solve the previous problem, we can use few shot prompting. And few shot prompting actually shows the models, the LLMs, some examples that we will provide and teach the model what to do and what not to do. And in this way, the model can actually handle these subtle cases or edge cases and produce the response that would be more accurate and more closely aligned to what we expect. However, this approach may also fail if if we are providing some bad examples and inconsistent examples, which would lead to some hallucinations or unexpected outcomes. And now let's take a look of a zero-shot prompting example. And this one just follow closely to the previous prompts. And what is new here is we're adding new examples here. Example 1, we are giving the LLM a new algebraic questions, and we are giving it also the corresponding answer, and we are giving it 2 examples before we ask our actual question, which is the last part. John has 10 books, and how many books does he have? As I mentioned before, if we are giving the LLM some really bad examples for demonstrations, it would not produce something that we want, which brings us to the next strategies that we can use is chain of thought, prompting for alignment. And in this strategy, chain of thoughts is mostly or commonly used for some more complex tasks that requires like multiple steps. And often when we're asking for LLM, prompting LLM, a direct answer is not sufficient enough. So this is where COT makes the model to actually encourage the LLMs to show the reasoning steps so that it can guide to a better output or response. And another advantage of using this is you can actually see what the LLM reasoning is behind instead of just throwing you an answer out of the blank, so that you can sort of understand whether the LLM is giving you something that is nonsense. And the other advantage is also you can pair this strategy with few shot prompting strategies to further escalate or to further improve the response improvement. So let's look at the zero-shot COT example. This is essentially the same with the zero-shot prompt example, except the highlighted part, which we added is we wanted to ask the LLM to give an answer and say, let's think step by step. And this simple phrase is actually really powerful, that it can encourage the models to show its reasoning before it gives you the final response or the answer, which often will improve the accuracy of the response. And as mentioned before, we can also fill in zero-shot with COT. And this is an example of it using the same previous prompt. And in this case, we're adding the reasoning steps into the few shot demos instead of just giving the answers. So here are some general guidelines that we suggest for doing prompt engineering for alignments. And obviously, if you are doing some very simple tasks or just some basic tasks, you don't want to overkill and use few shot or chain of thoughts, especially when you are using proprietary models such as ChatGPT or Cloud, because the input tokens actually can be costly. But if you're working with some tasks that it can be very hard to describe in words, you can use few shot prompting strategies to show some examples and the answer to guide the LLM to give you the response that you need. And lastly, for some very complex multi-step tasking, we'll encourage you to use chain of thought prompt strategies. And as mentioned before, you can always mix and match and use few shot COT or zero-shot COT, depending on the task or the budget that you have. So now we have go through like the 3 strategies here, but I guess like many of you have always come to the challenge where you have to adjust your prompts, put into LLMs, see the feedback, and then adjust the prompt again. And this manual process can be very tedious and time consuming. So this brings us to the approach that can solve the problem by using the automatic prompt engineering for alignment. So why do we want to automate it? Because a small changes in the prompt can actually drastically affect the LLM outputs. And manually checking the output safety at scale is not actually practical if you have a very low budget. So the workflow for this automatic prompt engineering is very simple. We just let the LLM generate the candidate prompts, and we will evaluate one of each of those, score them, and just pick the ones that behaves the best, that has the highest performance. So up till now, there are a lot of automatic prompt engineering libraries and framework, as I have listed a couple right here. This is the most recent ones. And the ones that we want to focus on is, as I mentioned before, the DSPy improvement optimizer, particularly the MI Pro V2 optimizer. So now I'm going to briefly introduce what DSPy is, and we want to use this as an example of the automatic prompt alignment methods. So DSPy is a library that can help you to actually write the prompt or to treat the prompt as a program instead of like the user have to manually type in the prompts entirely. So all you have to do is you simply define your task, your reasoning strategies, and DSPy will compile this information into a prompt. And furthermore, DSPy also have optimizers to sort of optimize these system prompts and fine-tune it to produce better performance based on user-provided training data and also user-defined metrics. So DSPy has three core elements, or you may call abstractions: the signature, the modules, and the optimizers. And these elements control the model's behavior, strategy, and the ability to improve the prompts. So here's how DSPy compiles the system prompt for you. The signature defines what the model should do. And we can just simply throw in simple instructions that, hey, I have some questions, you just give me the answer. And for the module, it defines how the LLM should do it. It actually tells the LLM what the response is, whether they can just respond it directly or just show me the reasoning steps. And together, we can use the signature and the module to generate the system prompt structure. And lastly, the optimizers would help optimize the sort of generated system prompt program to make the prompt better and produce a better LLM response. What it does is basically find the best demonstrations. It automatically would select the best few shot examples and provide instructions through your training data to sort of like adjust your prompts. And as a result, we will just a little recap. We will use the signature and the module to create the basic prompt structure, and we will use the optimizer to optimize this system prompt program to produce better results.
Tommy, can you clarify a system prompt versus a prompt that you use in ChatGPT? Like, what's the difference between prompting in ChatGPT or whatever versus a system prompt that you talk about?
Yes. So I guess for to my understanding, a system prompt is a sort of more like a high level or like a general guideline of what you would prompt the LLMs to do, have some structural format. Whereas if you just like give like a simple prompt, you would just type in like you talk to like a friend or something, instead of asking specifically what you want and giving instruction to it.
So how do those two interact? System prompt. So let's say we optimize system prompt here. How does it help me when I help the user when they're just prompting?
So I guess by actually optimizing the system prompts, it will sort of provide you I would say that
you append the system prompt with my prompt, and then together is the LLM produces the response, or what happens?
I'm sorry.
So what happens to my specific prompt? Let's say I want to say what's the capital of United States. That's not a system prompt, right?
That is not, yes.
So how is that related to the system prompt?
You can think of like a general prompt as a part of the system prompt. I guess the question that you just asked is what is the capital of the United States, which is I guess what I just showed you using a Google guideline, where this is the only the part of the task. But for a system prompt, we will also wanted to include a sort of like a persona that I just talked about. You assign the LLMs a person or a authority, and we will give more information based on the instructions. So I guess, yeah, that's the difference. Hopefully that addressed the question. Yeah, thank you, Theja. Yeah, going back to the DSPy course, as mentioned before, the signature would express what the user want the model to do. And there are two types or two ways to declare this signature. One is a simple shorthand version, and the other one is a class-based version. So a simple shorthand version is just like one line of code here, as I show you. You just declare DSPy.signature and have the inputs and the outputs that you want to specify. So this is usually used for some simple tasks or some fast iterations just to check how the LLM works or responds. Just give you like a fast sort of tries for fast alignment. And the second one is a more complex one. It's a class-based version where we will specifically define the signature as a class. Here, I called it a question answer class. And also in the doc strings that I give, read the question carefully and solve the questions. We can actually see it as like a mini theme or central theme of these signature or the prompts that you provide to DSPy. And obviously, you can also further declare or define the question types and the answer types and give specific instructions to it. And as you can see for the answer column, you can sort of provide information to keep the final answer concise with no units. And going along with the signature is the DSPy modules, which is the building block of the DSPy program. And the DSPy modules tells the model how to do and execute a signature. So should the LLM just give you the answer directly, or should it give you a step-by-step reasoning, or to use some other tools during the response process? The DSPy modules are very composable, which means that you can create multiple modules and chain together, depending on the task you want to do. And it is also optimizable, which means that you can use the DSPy optimizers to optimize these signature module created prompts to achieve a better performance automatically. So there are lots of built-in modules in DSPy, and today I'm going to share two of them, which is the predict module and the chain of thought module. So this is a simple example of the DSPy.predict modules. As you can see in the code, in the code, we declare the module and passing our shorthand signature to the module, and then run it just like a normal function. And we can obviously throw in a questions to this sort of a module and ask, oh, what is given 2x plus 3 equals 7, what is x? And it will produce the results for you based on the system prompt generated from the signature and the module. And as you can see here, we can take a closer look of what's behind the hood. This is the generated system prompts that DSPy will produce for you once you roll out the codes or define the variables. And this is pretty much what consistent with what we described. And we actually giving instructions manually, but DSPy is actually doing it automatically with a sort of like coherent structures here. And let's take a look for the other different modules where we switch to a chain of thought process. It is almost the same, but if you pay close attention to the highlighted part, the prompt is actually a reasoning, adding a reasoning section to both the output fields and the question field. And all you have to do is just write the 2 lines of code, and DSPy will generate this system prompt for you instead of having you manually writing it. And as mentioned before, there are a lot more modules, and you can explore depending on the task that you want to achieve. And I think DSPy actually has a lot of options and can be very flexible for prompt engineering tasks, for automatic prompt engineering tasks. And lastly, we'll go to the DSPy optimizer. So having a program built based on the signature and the modules, we will use the optimizers to improve the system prompts. And it sort of acts like optimizers to keep improving the programs when you are giving the program some training data in a specific metrics, and it will sort of go through the optimization process, let's say like 100 times until it and search for the best performance of the system prompt candidates. And this is very flexible because it totally replaces the trial and error approach when you just write the prompt manually. And in DSPy, there are several optimizers options. For the simple one is the bootstrap few shots, which simply just select the highest scores examples using a bootstrap approach. And the more advanced one is the MI Pro V2, JIPA, and the Simba. And for today's Python notebook tutorial, I will specifically focus on the MI Pro V2 optimizer. So every optimizer in DSPy needs 2 things: the training data and metrics. So for training data, you probably need 30 or to 300, and we usually want to keep this number low because we don't want to overfit the model. And we also need metric scores that can score the output quality. And there are some built-in metrics in DSPy, which is the answer exact match or semantic F1 score. And DSPy also has the flexibility for the users to create their own metrics functions if these built-ins don't actually meet your needs. And the other cool thing about DSPy is you can also call in an external LLM and use that as a evaluator to do a LLM as a judge. So this is just a code example of using the MI Pro V2 example here. Obviously, in this example, we are using ChatGPT 4o Mini, and we are using or running a data set of the math algebra data set. And as mentioned before, we will create a program using the DSPy chain of thought modules and a shorthand signature questions to answer. And then in the optimized part that we define, we will define the DSPy.MI Pro V2, throw in the metrics in it. And also in the module compiler, we want to throw in the training data set as highlighted in this slide. And once we optimize the program, we can evaluate how well the optimized program prompts behaves by using the eval function. So to sort of summarize what we just discussed, the automatic prompt engineering for alignment, it actually creates a loop, which means that you will just build your program, evaluate it, optimize it, and repeat the steps until it reaches whatever you decide the LLM produce as the outcome. And what's flexible about DSPy is within like this cycle of loops, you can always do some adjustments to it. For instance, maybe let's say if I run after the first run, I can add in some new training data to create the program again and see how well the optimizers will do to create a better system prompt. You can also switch modules, which means that originally, if you just use the predict modules, you can easily change the optimized modules to chain of thought modules and run the optimizer again. Also, you can change your metrics if you think that the metric is not reliable. And you can also run a different optimizer, or you can stack the optimizer, which means that when you first use Bootstrap few shots, you optimize the program, you can actually optimize this optimized program again with the other optimizer.
I have a comment, which is that the automatic prompt engineering part is actually not online, as in it's not at the session level. It's something which is off loop. So it's just like, fine tuning is off loop, right? It's not during when somebody's asking for a question or looking for an answer. So similarly, this whatever you're showing, automatic prompt engineering is something that is done off the loop, in the sense it's not during when users are actually asking questions for getting answers. Right?
Yes, it's still
There's
out there.
some computation needed to do this prompt engineering automation. So what does the computation need?
The computation, I guess, heavily puts on the optimization loop, depending on the algorithm that you choose.
So do you need GPUs? How many GPUs? How much? You're not touching the weights.
So to my experience, when I use DSPy, I don't need a very strong GPU. It only depends on the CPU. But you do need a strong GPU to host your local model, or unless you're using proprietary models. But most of this work can be done with just a CPU.
I have a question.
Yeah.
So you mean that most of this is can be done with a CPU, mean that you offload the coding the model to a APIs, right?
I'm sorry, can you repeat the question?
So the models, the LLMs, you need to produce the prompt, right?
Yes.
So if it's trying to produce the prompt, meaning that it has to be run on a GPU of some sort,
Yes.
right? So if it's done via CPUs, meaning that maybe you host a model via internal APIs or via like an enterprise API, right?
Yes.
But the loop is CPU.
Yeah, the loop is CPU. Yeah. Sorry. Yeah. Yeah, you're right, Asan. Yeah, thanks for clarifying that. So we still need the GPU. Oh, sorry.
Yeah, and a similar. So basically, the I will be part of the calling the modules and part of the local inference stack, right?
It's not. So that's what my initial point was that it's not part of the inference loop. It's basically equivalent to it's off the loop, in the sense, just like how you would take the LLM and do fine tuning. Here you take an LLM, do automatic prompt engineering, but the output of that is an optimized system prompt. Then you use it actually in real inference time.
So you have to
It's an offline optimization.
and then you have to take the output, optimize the
The
prompt,
output of
use
this
them.
output of this is a system prompt which is optimized for the task. Optimized doesn't align for the task.
And
So
then you can use them for the real.
Yeah, use that optimized aligned system prompt in online, and when people are actually querying or whatever the task is. Thank you.
Yeah, thank you for the question. Yeah. So for the next part, I kind of wanted to share some of our recent research work directly related to automatically prompt engineering that pipeline that we just discussed today. And the central questions of our case study is to ask, okay, so once we use DSPy and once we have this optimized prompt aligned, can we transfer this optimized prompt from one model to the other? And how the performance would look like. So that's the central, I guess, research question. So the motivation of our research is, I would say, is highly practical. Organizations always switch LLMs. When there's a new one or state-of-the-art models coming out, they would use that model, and obviously for some cost constraints or policy changes, they will also do model switchings. And optimizing prompts can be model specific, and these alignments that you do, for example, in DSPy, may not carry over to the other models. Let's say if you optimize a prompt using DSPy in ChatGPT, using that optimized prompt from ChatGPT may not behave or perform as well as running it on Cloud or Gemini models. So re-optimizing this optimized prompt can be very expensive. So the goal of the research is to measure how aligned these prompts can transfer across LLMs. So we are asking two sub-questions. The first question is, as I mentioned before, you take a prompt from it. When you take a prompt optimized for one model and apply it to a different model, do they still perform well? And the second question is, if a model has a strong baseline performance, does it produce a line prompt that works better for the other model as well? So this is how we set up the experiment. It is a two-step process. Well, first step is the align step, which we optimize the prompt on the source model for a specific step. We will take the exact optimized prompt and apply it to a different model and see how well it performs for the same task. And we repeat these process evaluations a couple of times, n times, because every single time when you prompt LLM, it will produce something different, which behaves just like a random variable. And we will report the average score. And to clarify, we define self-aligned as a model uses the prompt optimized for itself. And for cross-aligned, meaning the model uses a prompt aligned on the different models. Quantitatively measured this alignment transfer difference. We are sort of like proposing a metric called the prompt transferability index, PTI, which simply just subtract the cross-aligned score by the self-aligned score. And if the PTI is greater than 0, we'll call that the transfer alignment improved performance when you are transferring to a different model. Whereas if it's smaller than 0, we'll say that it has a degraded performance. See any significance. We obviously, since we're running this multiple times, we will use a statistical test, which is the log ransom test, to confirm whether there are statistically different. So for the experiments, we focus on using MI Pro V2 and Simba Optimizer from DSPy and test this across 3 model families, ChatGPT 4.1 Mini, Gemini, and the Llama model. And we use the zero-shot chain of thought baseline, our baseline performance. And we ran 2 data set or 2 tasks. The first one is the medical calculation benchmark, which is the reasoning data set for doing medical calculation. And the second part is, and the second task is the MAT-EC, which is the clinical error detection using Simba as the optimizer. What we find is to answer the first questions, to answer the first question, when you're taking the optimized prompt from one model and apply to the other one, it actually does not perform as same as the previous model. And based on our study, we often see like degradation compared to the self-aligned prompts. Yes. Yes, compared to the baseline, yes. And for the second question, if a model has a strong baseline, it actually does not produce a, and often we observe that models with weaker baseline performance can generate better transferable aligned prompts.
Wait.
Yes.
What, roughly, how much was drop on performance of the alignment? So are we talking about half of it, 50% drop or more?
Yeah, so I'll just give you a quick, I guess, like summary for the first experiment. We are seeing about 6 to 7% performance difference when we are transferring the optimized prompt from GPT to Gemini 2.5. Thank you for the question. So for our case study is the aligned prompt don't actually fully transfer, which means that switching models when we are doing automatic prompt engineering, can actually break the alignments. So model upgrades or switching these models will require to realign, and it adds a lot of cost to it.
I'm kind of curious, if it is the same model architecture, why should it break the alignment? Different why would it break?
That's a good question. I actually have a different set of experiments that I ran to control the model family type, and we actually observed that when we're using a high parameters transferring to a lower parameter models within the same family. I hope that answers your question.
You could put that as a caveat, right?
Yeah.
So I think has more information posted. But I would say even if it's the same family, let's say 7 billion parameter with a 13 billion parameter model, it's the same architecture, but we're saying the weights are different, but that should not affect alignment. Is that your intuition?
Alignment is doing something. If it is doing something, it better stay there.
Alignment is
not doing that,
it's not touching
it's a
the
useless thing.
no alignment is not touching the weights, right? It's doing something in the sense of prompt engineering in this case.
No, so whatever it is doing, it better stay that way. Because if I change the model sizes and everything, right? I want that.
Fine, I agree with you. We would want consistency, right? We want robustness. But this is what we observe today with existing open weights models are close to, this is what we observe, right? So if you desire robustness, then maybe we have to prove that.
So here's my other question. Sorry. If I align on a larger parameter, and I try to transfer it to a lower parameter, will it stay?
That's a great question. You should go to his poster. He's done all those experiments. He must just not capturing it.
No, so, but what's that?
Yeah. Due to the answer is yes. The performance will stay.
At least something stays.
Yeah. Thank you.
I want to keep going on the trade, but you got do it on like a model with like checkpoints.
I'm sorry.
You can really have like you can like same problem. Like if you know like brain.
Oh, that we have not done. Yeah, but that's a great comment. Okay, thanks for that. Yes.
First aligning on like the smallest model and then get it up and then align it.
Question. All these questions, I actually in my poster section, I have run experience on that. But to give you a short answer, we observe that we don't necessarily need to align with the biggest model. In my experiment, when I align with the middle ones, as well as align the so it really depends on the family, the model family type. But what I try is the open source model, Gemma 3 and Gemma 3, yeah. Yes.
Is that from between models related to model evaluation, we compare reasoning abilities across different models, how can we make the evaluation system is clear? How to make a peer comparison between models?
And I declared the DSPy program. I will just fix the baseline using chain of thoughts or just like zero shot prompting. But I guess for the inference part, as you mentioned, some models would have the inherent control. Just let whatever evaluate on that part. Yes.
What can be the root cause of this? Is it the different prompting styles in which the data is prepared by different family of models? Different variations in the family of models are doing the alignment of the brain. What aspect of training that is something that you can look at is point of kind of data.
I mean, I guess your question is why why doesn't alignment transfer? What's the cause of it? He's measuring that there is, alignment doesn't transfer. And, generally you can go and say, okay, alignment doesn't transfer, then how do I fix it? Right? And how to fix it might involve knowing the cause of why alignment doesn't transfer. But I don't think he has studied that. But it's very easy to imagine that, these are functions and you train and do training, which is before all these alignment exercises, you can get to some parameter weights for two different models or architectures or whatnot. And it's very natural to expect that they would not have the same alignment performance. I feel like that is a natural expectation that they should not be having the same performance. The question is, how much is the gap? I mean, if they're really good, then they should not be sensitive to how you prompt. But what we observe today is that they are sensitive to prompt, and therefore we are optimizing and also trying to understand how to transfer.
Are these what you see learning? We saw, right? So that was always observed from early on, as you were saying, like functions, right? So you may end up learning a slightly different functions every single time, so then the sensitivity of that time.
Yeah, it's related to adversarial robustness. It's related to adversarial example. You have a question?
Yes. I don't remember. If you measure that standard performance of your final output.
Yeah, so maybe he'll show the notebook. He'll just quickly walk through and
Yeah, so I'm curious if you have this alignment optimized system around, right?
Yes.
You
there's a number before, there's a number after, and you have to see the measurable.
Yeah, I guess this goes back to this slide. Actually, yeah, we actually do have a baseline measurements to it compared to the optimized score. I guess I'll get to the notebook. Hopefully that would clarify some. Yeah, so as Theja mentioned before, I'm presenting a poster. I guess that would hopefully answer some of the questions that you addressed here, and I would appreciate if we can continue the discussion on the case study research. And now we're moving on to a live demo with a Python notebook. If you might now go to the GitHub link and download the notebook, just take a minute. Oh, yeah, you need to click on the collab button. Yeah, sorry. There's a collab button. Yeah, let me just go to the website here real quick. Yeah, I guess yeah, don't click on the stuff above. There should be a collab button here, open in collab, and you can open the notebook in Google Colab. The code are customized for a free T4 GPU on Colab. The notebook on a higher or a better GPU to get a faster response. Has book. Yeah, I'll just briefly go through what I have to. So the notebook tutorial outline basically what we wanted to show today is how do you hope? Yes. Oh yeah, sorry. Okay, great. So let's go to the notebook. As mentioned before, so for this notebook tutorial, we want to show you a few things other than just DSPy. The first one is hosting a local LLMs using VLLM on Colab or any local machine. And we'll go through some basic DSPy modules and signature declarations that we show in the slides, and to sort of build the program and use the MI Pro V2 optimizers to optimize the program. And we will use the GSM8K math dataset as example. So hopefully, yeah, you all get to the Google Colab notebook. So first we will install the required package. So one quick note on this is we need to install a previous version or the lower version of the VLLM transformers and Hugging Face, because the higher version or the most updated version is not compatible with T4 GPU. So this is why we're doing this. So once you install these packages, you need to restart. Hopefully, yeah, you need to restart the section just to let the install package to load in. And to host a local LLM, yes.
There's one command that is commented out that you need to run LLM serve.
Oh yeah.
It's to be in a sense.
Okay. Oh, I'm sorry. Yeah, I'll just do it here. Yeah, so I guess yeah, thank you, Theja. So to host a LLM VLLM on Colab, you need to type in this command VLLM serve Nguyen 2.5 into the terminal window, which you can click on the button below and type in this command, and it's going to take maybe like a few minutes to sort of load the server. I guess while we're waiting, I guess for the VLLM to be online on the Colab, I'll just briefly go through the rest of the code. So next off, we will import DSPy, and we will use the curl command to check whether we have actually hosted the Nguyen 2.53B model in our Colab server. And in the next cell, we will define a LM object using the dspy.lm. And in the model specification, we want to do OpenAI/Nguyen 2.5. The reason why we need the OpenAI in front is because DSPy is using a OpenAI style API, point-based sort of like style. So that's why we need to add this. And the API base, we just need to add the address that we hosted locally in the Colab, which is the localhost 8000 v1. And for API key, you can just put in any strings because we're not actually calling the real actual API. And for cache, you can set it to true, but I set it to false here because when we are doing evaluations, I guess I wanted to see how the LLM actually performs without like memorizing the response before. So this is why I put cache equals false. And temperature I set equals to 1, just to allow the LLM to have some randomness when it is generating the optimized prompt.
Yeah, people are facing issues. Once he finishes the walkthrough, as we will come across, we will come around and how do you? Go ahead. Action. Where do I get this? Which is this the Google collateral or Google collateral? Okay. Yeah, let me take it over.
Okay, yeah, I'll just finish and come address the question. So in this cell we will declare the LLM models using the Nguyen model from VLLM, and we can quickly just do a call and ask the Nguyen to give us some response. Here I just do a simple question, which is 2 + 2, and it gives me this 4. And in the next cell, I am importing DSPy and the GSM8K dataset along with the DSPy defined metric. And here are just like some specifications for the GSM8K dataset, along with creating the eval function, which is the DSPy.eval. And in the evaluation set, we are only considering 100 data points, just for some fast experiments. And for the metrics part, we are using and for the metrics part, we're using the GSM 8K metric that is already defined in the DSPy library. So we can actually take a close look of what the GSM 8K metric is. So basically, this program is just like stripping the LLM response with all those like unnecessary words and only extract the numbers or the numerical answer from it. And moving on to the building the DSPy program, as we mentioned before, to build a program, we need the signature and the module. And in the example here, I'm using a shorthand string version questions to answer and create my zero-shot program called program_zero-shot using just the predict module with a shorthand signature. Same for the other one, I create another program called program_COT using the chain of thought module. And now once we create the program, we can use our evaluate function that we defined previously to test what the baseline performance is. So for the zero-shot program, we're only getting 25%, which is not very satisfactory. But when we look at the chain of thought program, the metric score actually improves by a lot, almost like double of it, like 57%. And if you also pay close attention to the display table, you can also see the reasoning that the LLM is doing behind the scene in the column for each test set question. And alternatively, as I mentioned before, you can also do a Python class-based signature, which means that you will create the signature as a class. That are defined here, I call it GSM 8K signature, and I will pass the DSPy signature. And in this class-based signature, I will have a doc string, which sort of serves as like a central theme of the instruction. You're a math teacher, answer the math question with numerical answers. I also put on some additional specifications for the input fields and the output fields. And we use that, we can also use this newly declared program to create the zero-shot baseline program, zero-shot program, and the chain of thought program. So for this cell, just evaluating it, and you can see the performance is similar to what we saw by just using the shorthand declaration. And further, once you evaluate the program, you can inspect the system prompt by calling dspy.inspect history n equals to 1, and it will provide the system prompt and the LLM response. And same for the chain of thought modules. We evaluated has a lot higher performance than the zero-shot program, and we can also inspect the system prompt once we eval this chain of thought program. And as I showed in the slides previously, one key difference of the system prompt is for the chain of thought program, it has the reasoning part in the system prompt, as you can see here. And in the actual response, the LM is actually showing the reasoning steps too. And now going to the optimizer. As mentioned before, I'm using MI Pro V2 optimizer here. Is using the bootstrap technique and also some algorithms to optimize the program. And in this cell, I'm just declaring the parameter, the optimizer, which is called by dspy.mi-pro-v2 use. And I set auto to light just for some fast runs. And I also limited the few shot demos to 4. And once we define the optimizer, we can actually compile the optimizer using the previous program that we created. In case I'm optimizing the custom-based signature chain of thought module. And this often take like 15 minutes or more, depending on the number of demos. You can see it's actually picking a. And once we have optimized, sort of check the performance by doing eval optimize DSPy program. And as you can see, we're actually getting even better metric score, 69%, compared to the previous just chain of thought program, which is just only 63%. So I guess the moral of the story or the take message here is without doing fine tuning or like retraining the model, we can still improve the LLM response by just doing automatic prompt engineering here, which is sort of relatively fast and also a lot less costly. So finally, okay, before that, we wanted to inspect the optimized system prompt. So essentially, everything is the same, except that we can see this system prompt is the similar structure as I showed you before of the few shot chain of thought prompting strategies here. The new system prompts is adding example questions with reasoning. And here I have like 4 examples here before I prompt the LLM for the questions. And we can also specifically extract these few shot demos using the .predict.demos command. It produces a JSON format to that. And last but not least, once you optimize the program, you can also like save this program for future use. And I've showed the code here. And you can, once you save it, you can always reload it and actually play around with it with the other data set, or maybe try a different optimizer and build on top of it from scratch instead of starting from scratch. So this ends the part of section here. Thank you so much for your attention.
Yeah, and if you're trying it out, let us know if you're hitting any bottlenecks. We do have extra VMs with some GPUs. If you don't want to use collab, we have GPU with these. let us know. Otherwise, we'll break in 5 minutes for a break is coffee break and resume at 3:30.
Thank you so much.
Thank you.
All right, everyone. I hope you had a good break. All right, so I have pushed the slides to the GitHub that we have, right? So if you want to, please go to the slides and take a look at the slides as well. Okay. All right. So we should. All right. So we should get started with the next section. All right. So. For next one, we're gonna talk about guided decoding. So as of now, so everyone know about prompt engineering already, right? So have anyone heard about guided decoding before? You have heard? Okay. How about the next one? Response engineering. No? How about best of N? How about self-consistency? Okay, so we're gonna go through those. Okay, but first let's get started with guided decoding. All right. So with prompt engineering, what you do is before the model generating your output, you are trying to steer it, right? And then put it to the model. The model spit out some output. With guided decoding, what we want to do is we want to control it when it's decoded, when the model is decoded token by token, right? So first question we want to go through is how LLMs generated text. Okay, as everyone know, is generated text in an auto-recursive way, right? It's meaning that it's generate one token at a time, right? And then it keep appending the output of the last time step to the input of the current time step. Okay, so at each step, the model outputs a probability distribution over all of the tokens, and then a decoding strategy decides to pick which token, right, gonna be output to the user. So this repeat until you have the complete output. So the choice of the decoding strategy affects the quality of the output, diversity, as well as speed. So here are some standard decoding strategies, right? From the deterministic to stochastic. Deterministic meaning you may have greedy search strategy, or you can have beam search strategy, right? For stochastic, you try to introduce a little bit of random in there using temperature, top K or top P. Hopefully you guys also using that in your when you interact with LLMs, right? Beside the APIs. All right, so these are built-in strategies, but there are no guarantees about output structure and alignment because it's working directly with the logic, with the probability of the weights, right? The training model, the model after train, right? So let's go over a little bit of basics. Go back to the basics. What is ready decoding? Okay, so the idea here is it always pick the token as each time step, pick the token with the highest probability, right? That probability is a output of whatever you are trying to train when you do training, right? So the properties of this decoding strategy is fast, right? It's good for structured tasks, but it can get stuck in a very repetitive loops, and it misses globally better sequences, right? Because each time step, it's just getting the next best token, the next best token. Okay, so an example for this is the earlier language model usually for this is just keep saying the sky is blue, the sky is blue, the sky is blue. All right, so the next one is beam search. So the idea of beam search is that instead of just select the best one each time, you select K partial creases at each step, right? For example, if you look at the image here, we see that, for example, I set my K equal to 2. So at each step, it's going to select 2 highest tokens, right? So for example, here, it select 0.5, 0.4 here, okay? Then next step is going to, from the nodes that is selected, it's going to keep selecting 2, K equal 2, right? So here and here, and then we can see that, for example, these 2 nodes have highest probability. So it's keep doing that forward, okay? So next, so what you see that with beam search is that is very deterministic, right? Model output something, some probabilities, and then we select, right? So if that's the case, then always you're going to receive the same sequences, right? Because there are no random, there's no stochastic. Therefore, people have been trying to do temperature scaling. I hope that everyone heard about temperature in language models, right? Okay, when you put temperature equal to 0, what happened? Excuse me? Deterministic, or because when you get low temperature, right, the distribution become very picky, like this. Therefore, it's always keep getting the same thing. So it's become very precise, right? However, when you set the temperature to very high number, your probability distribution start to iron out, right? So you have greater chance to pick alternatives as well, okay? So it's used to control creativity versus precision, or diversity versus precision, correct? All right. So the next one, people have been trying to do top K sampling. What is top K? Top K is just instead of introducing instead of temperature, is keep the top K most probable tokens, right? In a single step, right? So for example, my K here can be 4. So it keep 4 tokens, highest token, and then randomly select from them. Okay, instead of select the best one, it skip K and then select the best one. The random one. All right. So it's cuts out the long tails of the unlikely tokens. If you set small K, it's very conservative, right? Because you only select the top few tokens. If you select a large K, meaning that you are considering a diverse number of tokens. All right. So if you fix K, so the fixed K, ignore the shape distribution, right? It's always, okay, 5. No matter what the distribution is, I will just have 4, like for example, like this, 4K, even though I may have other distribution, okay? And the last one for standard decoding techniques is top P sampling or nucleus sampling. So the idea of it is keep the smallest set of tokens whose the cumulative probability exceed P threshold, right? For example, right here I have top P is top 0.9. So for example, I have a very picky distribution right here. These 3 tokens already account over 90% of my cumulative distribution, the probability, right? So it's gonna select these 3 and then randomly pick one of the 3. Okay, so that's why there's like a randomness inside, right? Otherwise, it's just gonna be the same sequences over time. Go ahead. Yes. Yes, with uniform probability, right? So and then for example, if you have some fat tail distribution like this, 0.9 might be account for a large amount of tokens. So therefore, you are able to choose diverse set of tokens. Okay, so it's more robust than top K because it adapts dynamically to the distribution shape, right? It's used probability instead of number of tokens to keep. Okay, here are some pros and cons, right, of standard sampling. But the thing I would like to highlight here is that none of these prevent hallucination, unsafe outputs, or structural violations. None of this guarantee you to have alignment. The reason is it uses the probabilities or the logics of the trained model, right? It uses the internal signal, right? And then it's not able to incorporate extra signal outside, external signal. So that is why we are moving from normal sampling to guided sampling or guided decoding. So the idea of guided decoding is that instead of using the internal signal, now you're using the external signal, right? You can use reward model, you can use verifier, you can use a constrain, and then you attach that directly into the decoding, meaning when it's trying to generate, you try to steer that in that stage, steer the generation in that stage. All right. So where does guided decoding fit? So we are here, right? So we are doing it in generation. Okay. So I would like to talk about three main types of guided decoding that you may find useful. One is logic processor. So it's operate under in token level biasing, right? One is constrain decoding. It's good for grammar schema enforcement. And the last one is tree search decoding, including beam search. Plus, instead of using a probability of the model, we use a verifier or an external reward model, as well as multi-color tree search. All right.
Can you clarify, can you use these techniques for closed source model? Let's say I'm using opening API and I want to do this alignment task for my application. Can I use these?
You can use it for tree search decoding, but not for logic processor and constraint decoding, because they need to access the token level or logic of the when the token of the tokens, right?
It's only open weight model.
Open weight model, or the one that provide a very detailed API where you can have access to the logic. Okay, but that's really rare. I haven't seen one that provided logic level yet. All right. So yeah, so let's talk about the first technique in guided decoding called logic processors or token biasing. So this is extremely useful because it has a wide application, right? So after the model produces logics, we directly modify them before sampling, right? So we boost the probability of desired tokens. For example, if you wanna have like a classifier only answers yes and no instead of like open-ended responses, you can boost the probability of yes and no higher artificially, right? So for example, here before, this is what we may observe, right? But you may, okay, this plus 20 for yes, plus 20 for no. You're only interested in two tokens, right? Yes and no, because you are trying to build a classifier. So if you do this, then your model gonna output just yes and no, right? Also, you can suppress probability of forbidden tokens. For example, you don't want to say curse words, right? So you can always suppress that probability down, so the model never gonna choose that word or token. Okay. And another one is you can also do hard mask, right? Set the token to negative infinity. So forced exclusion or fallback. The use case for this is, for example, you wanna build a classifier that only answer 2 tokens or 2 output, yes, no. You wanna ban toxic words, and you wanna fall back on phrases or low confidence sentences or responses to prevent hallucination. Okay. So a concrete example for this is a sentiment classifier that must output positive, negative, or neutral, nothing else. How you do it with a language model, right? With a classifier, I mean, you have 2 or 3 classes. You set it before training. Therefore, you only have the 2 or 3 classes for discriminative learning, right? For this, you can do this by artificially boosting the probability of positive, negative, and neutral, like this, right? So I love this product. If you don't use this, it may, even though if you can prompt it, right? Only output positive, negative, and neutral, but the language model not always gonna follow your instruction in the prompt. Have anyone experienced that? Yes, right? Okay. That's why it's very hard to parse the result of language model into like some downstream system, right? All right. So the measure, we can measure here this with exact match, right? So you can your score can come from 0.62, so 62% to 100% percentage with 38% alignment improvement. You can measure it that way quantitatively. The next one is constraint decoding. So it's a little bit different than logic processing. Is that this is absolute, meaning that at each stage you have a set of tokens that the model must output. For example, if you want to output a JSON schema, right? So first one, you're only able to select this symbol because JSON schema started with this symbol, correct? And then the next one. So at the end, you have a valid JSON, okay? So everyone try structure outputting of OpenAI before, right? They're using this, okay? So this is very useful, right? Because when we ask a language model to extract patient info from a clinical node at structured JSON, again, it may not able to do that. It may just output blank text like this. And that is unaligned behavior, right? So using this, you can output an actual JSON scheme. So next one is tree search decoding. So this is one of the most powerful technique, but it's also one of the most expensive in terms of compute during inference. Okay, so instead of one greedy path like before, we explore the generation tree, right? Using verifier or a reward model. So one of this, you can use beam search with an extra reward model, external reward model. So you keep the top K partial sequences, score at each step, exactly like beam search, but change the logic or probabilities with the reward model, right? Next one is Monte Carlo tree search. Is anyone heard of Monte Carlo tree search? It's very popular, right? Back when Go, right? DeepMind. Okay. So Monte Carlo tree search uses sequences of steps like select, expand, simulate to the bottom, get the reward, back propagate, right? It's smarter, but then it's also very expensive. Okay. So alignment for this is you can use it for math, reasoning, code generation, any task that requires step level verifier. You can break it into steps, right? Or sentences. All right. So a concrete example of this is ready decoding. When you do ready decoding, when it's read, when the model get wrong at any step, it's keep going, right? So the error keep cascading. But with beam search and step verifier, it's gonna get the one. So for example, when it's going to step 2, and then there's something wrong with it, it's gonna keep exploring until it get the correct one, and then keep going. All right. So, sure.
The very high case would be.
It can be another LLM, another reward model. Reward model, you can think it of a classifier, positive, negative, right? It also can be human as well, if you have human in the loop, right? So to compare these techniques, so the cost, right, going from very low to high, right? But the limitation is for logic processor, it can only be done in vocabulary level only. For constraint decoding, you need grammar spec, right? Okay, you wanna do it in JSON format. You wanna do it in X and X and Y format. You have to specify it beforehand. For tree search, you need to have a step verifier, okay, which is also very expensive and hard to obtain. So the choice here, depending on the alignment goal, right? The latency budget and also your compute. All right. So you can use multiple metrics for these. For example, logic processor, you may use exact match for measuring alignment. Okay. For constraint decoding, you can use F1 and validity to check. For tree search, you can use step level accuracy to check your alignment. Okay, so summary, just show you 3 main techniques for guided decoding, which is logic processor, constraint decoding, and tree search. Okay, and now I would like to go over the hands-on practice for this section, but I would like to be able to show it to you. So you don't need to execute it, right? Just focusing on my explanation. And then afterward, when we have time, we can execute it together, right? So that the flow not getting disrupted. Okay. All right, so please visit the same GitHub repo, and then click on guided decoding. Okay, so I already pre-ran this, so you still receive the output of whatever I was running, right? So you still able to understand this thing. All right, so you wanna talk to? All right. So for guided decoding, the first part I wanna do is just to introduce you with some standard decoding strategies, right, with VLLM. And the second part is actually using logic processors. Okay, and the thing is that this, because of the limitation of VLLM, because they're changing from V0 to V1, therefore the logic processor in the VLM is not comparable with V1, right? So you may need to run it in Collab Pro or L4 GPU. As well, we also have some compute, right? VM. Yeah, so later on you can try that out. Okay, but this requires Google Colab Pro. Okay. So anything better than L4 GPU gonna work. Okay, not T4 for this part. All right, so first of all, let's set it up following the same VOM setup, right? We have, but remember to use VM use V1 equals 0 because we don't want V1. Okay. All right, and then here are some helpers. All right, so first of all, greedy decoding. How do you do that in VLLM, right? It's just as simple, right? Just prompt with temperature equals 0. That's it. Then my prompt is what is the capital of France? Is our capital of France in Paris? Okay, that's easy. For beam search, I can use the extra params right here. Beam width equal 4, meaning that at each step, I select 4 tokens, best tokens. Okay, and then this is how I do beam search. For temperature scaling, it's very simple. In the extra params, you can just select a temperature. Here, I run a for loop with temperature 0, 0.7, and 1.5 so that you can see the differences between them. All right, so if I run 0 multiple times, meaning I would get similar result multiple times, correct? Right? But if I run 0.7 or 1.5 temperature right here, most likely every single time I will receive a very different results. Okay. So for top K and top P, also very simple. You can just set a parameter top K equals something. Right here, I'll do 50. And then top P equals 0.9 or 90%. Okay, and then this is what you get. Okay, very simple with VLLM. So you can just run this top down. It's just gonna work. But the thing is you need to have like L4 or above for this. Okay, and then going to part 2, where I'm going over guided decoding with logic processors. So again, the model gonna output some logics. And then we're gonna alter or manipulate that logic directly, right? Before you sampling, right? Before you doing temperature, top P, top K, okay? We do it before that. Okay, so for example here, I have a problem. Standard decoding has no mechanism to refuse a question. Therefore, hallucination, right? Maybe it can be trained on that to improve it a little bit, but most cases, it's failed to refuse. It's just keep outputting, right? The model always generates something, right? Even if it should not, it should not know the answer, but it still know the answer somehow. But if the answer is wrong or hallucinated. Okay, solution, you can use a logic processor here to monitor the peak token probability, right? And then at each decoding step, and then if the max of the submax of the logics fall below some threshold in some consecutive times, then you can flag it at insufficient confidence, or the model is unsure about something. Okay, so if you do that, then you have a mechanism to flag that, right? Basically a classifier. Go ahead. So it's based on the probability of based on the probability of the model. The heuristic is it's based on the training data. It is. Right, but yeah. So the model gonna output some logics. You do submax to get probability. You check the max. So basically heuristic, right? All right, so then I have a class of prevent hallucination, then stop. right? So I have do it here. So you can execute this, and then you can configure your processor, the hallucination processor. So you have, okay, if this, if the maximum of the submax of my logits less than some threshold, min probability right here, over some consecutive times, right? That's the tolerate right here, right? Then you flag it, you fall back at, wait a minute, I'm not confident about this answer. Please check other sources. Okay, so if I run this and then I evaluate on my evaluation data set, which consists of well-known facts, which the model is supposed to know the answer, obscure real questions, is documented, but it's rarely known. Model may start to think sideways, or fabricated entities, meaning that the request is completely make up, right? So I have it here. So well-known fact questions with attached route truth to measure the performance. Okay, so for example, who invented telephone? Everyone knows it's Bell, right? For obscure real question, so who invented the first practical submarine in 1814? So the route truth answer for this is no practical submarine was invented in 1814. Okay? For fabricated entities or hallucination traps, I would say. So I say, okay, let me select one that is fun. Okay, who invented the search engine WebSeer in 1994? I don't think that exists at all, right? All right, so let's run it side by side, right? To evaluate it. And then this is what I have, right? So here is passed because my first question is real fact, right? It's who invented telephone? Bell, right? So the baseline here is right here. And then the protectors right here. So pass meaning that there's no fallback, right? No flag, okay? But if you scroll down, it's starting to trigger, right? So who painted Mona Lisa? So the truth is Leonardo da Vinci. The baseline is like, which is Leonardo da Vinci, right? And then the protectors is like, okay, it's Da Vinci, but then it keep going. And then whenever it's saying, okay, I'm not sure about this, it's flagging. Oh, wait a minute, I'm not sure, confidence about it. Please check other sources. So this is an example of false positive, right? Because right here, for this example, I'm trying to set my tolerate very low, right? So just one, right? So meaning if you see two consecutive low probabilities tokens, you flag it. You may set it higher. Okay. That is it. And then if you go down, you may see that it's trigger more and more, right? So who invented WebSeer? Route truth is no engine exists, but the baseline, the model would have been answered David Philo. I don't know who David Philo is, and same day, 1994, and then it just keep hallucinating. You see the hallucination? But with my logic processor, when it gets generated to here, it's like, okay, we are not sure about this. Therefore, okay, wait a minute, I'm not confident about this. Check other sources. Okay, so you can see these examples inside the notebook. Okay, the URL code can also try your own question over here. And then the summary is each of this greedy beam search temperature top P top K logic processor can do different things, right? So one can control argmax overloaded. One is search over sequences. So the other one scale logic sharpness. Top P, top K truncates the vocabulary. The logic processor here modify the logic directly, right? So we can use it appropriately. And then here are some resources that you can also use. For some example, you can also choose you can also do a logic processor based on length of the answer. You want long or you want short answer. You can do citation. You can do hallucination. You can do a lot of stuff with this. Okay. If you want to know more about logic processor, I recommend you to visit NVIDIA Logic Processor Zoo, where they kind of build similar kind of processors. Okay. And then also VOM documentation. All right. Any questions? All right. If there's no question, I'll keep going to response engineering. Okay. All right. So I have asked this question before, right? A lot of people know about prompt engineering for sure, right? Even before this tutorial, right? Yeah. So, but I feel like not a lot of people pay attention on response engineering or best of n, self consistency, those type of optimization. Okay. So here we're gonna go over what is response engineering so that people have a better understanding of it and then find a use for it. Okay. So guided decoding steer generation during outputting or during generation, but response engineering intervene after the fact. So both post hoc. So after the output is produced, right? So you apply external checks, revisions, filters to align the final response. Okay. So here at the figure, you can see, okay, you have the prompt, you put it into the model output and response, you filter, you re-rank, you refine, so that your final response is actually good or actually aligned with your expectation. Okay. So where does it fit? So it's at the last step of the pipeline, right? After our output exists, then you do the response engineering. Okay. There are two main types of response engineering. One is static. The other one is interactive. So static is single pass. There's no optimization loop. So you use guardrails, filtering, re-rank and selection, refine, and then routing, right? Grounding, right? For interactive, you are attaching an optimization loop, right? You are starting to do reflection, which is refine, but again and again and again. Okay. You can do my evolution. You do LLM refine. You can do mixture of agents. Those are the papers that I think is important, right? And also I'll work on Memetron, which is a technique for iterative response engineering. Okay. Okay. First part for this, we're gonna get into static response engineering. Right? Some basics as always. Single pass, no feedback loop, right? So it's content of guardrailing, filtering, re-ranking, selection, refinement, and grounding. Okay, so here's some example of guardrailing, right? So customer support, the task is customer support chatbot. The output is, this company is very terrible, just quit. So a toxic classifier would classify this as very toxic, right? 0.951 point for toxicity. So we should block this. Okay, so when we block this, we can fall back into like, okay, to cancel, please do this, do this, do this, all right? For constitutional AI, so instead of a real model, you are actually as a language model, right? So there's some thing called constitution, meaning that the rules that most people believe is correct, right? So for example, a general assistant output just ignore them and make their work life difficult. So it's gonna check, okay, this violates be harmless, right? Please revise it. Okay. So and then the model is gonna revise the answer to, okay, try a calm, direct conversation, escalate to HR if needed. Okay. So you can see that form a very harmful output, it revises to a harmless output. Okay, so here is for re-ranking and selection. There are a couple of methods. So re-ranking based of n, meaning that you are outputting 10, 20 answers and then choosing the best of them. Yeah, you can use reward model, you can use constitution, no AI, you can use human to get the best of n. You can use self-consistency, meaning that you are extracting the common answers and then select that as a correct answer or the most correct answer. Another heuristic. You can use sampling, outputting 10, 50, 20 responses, ask another AI to synthesize those into a single response, and hopefully it's going to be the best. Okay, so here are some examples. Just gonna quickly going over this, right? So really for best of n, maybe inflation is caused by printing too much money, right? It's oversimplified inflation. So with best of 5 or best of n, it's gonna generate multiple answers, and then inside that answer, maybe there's an answer that inflation results from demand exceeding supply, rising costs, and monetary expansion. And hopefully a reward model or an LLM can pick it up, right, as the best response, and then output this response. Okay. For self-consistency, it's just a single one and for a math reasoning can answer and math answer 24. However, if we generate 10 samples and then do majority vote, you see 32 as an answer that have 7 out of 10 agreement across answers. Therefore, it's more robust, no score needed, which is a heuristic, but you can also achieve some accuracy or some performance out of that as well. Now on an assembling, so you can use GPT-4 to do some diagnostic, right? You can use Llama to do the same type of diagnostic, Gemini as well, and then combine them together. Okay, so it reduces overconfidence. All right. For group 3, it's about refinement and grounding. So refinement is about self-critique, right? It's going to be the model start to critique its own output and produce an improved version. Okay, so you can generate initial response, and then you ask the model going to ask itself what's wrong with the above, right? And then it start to analyze and rewrite to fix those issues. Okay. So no external model needed. Targets specifically on alignment, right? Because you are asking what is wrong with it, right? So the model may miss its own errors, right? It may be biased toward its answer, even though there's an error, but it's try to ignore it, right? And also add latency. Okay. For fact checking and grounding, you can actually use a RAG with a database to actually check for factual information, right? So it's routed in evidence. It's ideal for high-stake tasks, but it requires retrieval infrastructure, right? You have to build a RAG system. Okay, here's some examples. So the task here for self-refinement can be writing a professional email, right? A draft can say, hey, you still haven't replied, please respond ASAP. So it's not very, very professional. So it's like a very passive aggressive. So you ask us, oh, what's wrong with, given the task is to write a professional email and this response, what do you think about it? What's wrong with it? And can you refine it? So it can do some sort of self-refine, doing professional email afterward, right? For fact checking, we can use RAG, right? So you for medical question and answer, you don't want model to be hallucinated, answering the wrong information, right? Outputting the wrong information. So the output before is vitamin D dose is 1,000 IU for all adults. But with the retrieval of the medical database, you may be able to get the revised response saying that per NAIRR, adults per under 70 need 600, over 70 needs 800. Okay, so it's routed, age appropriate kind of stuff. Okay. Any question regarding the basics of response engineering? Just static engineering.
I would add one comment that the RAG file probably on the
It's in my opinion, response engineering is when your output changes, right? You can do prompt, you can do prompting to retrieve something, right? But the answer changes. The answer of before is unaligned, the answer after is aligned. Go ahead.
What do you use to calculate the human preference factor after what particular tool or scoring? I understand how you got what.
No, it's just an example.
Oh, okay.
It's just an example, but there are actually we can actually build a factual accuracy, some sort of reward model, right? To do this. For human preference, that's not verifiable, right? Human preference, so it's
a tool that yeah, so that's always
yeah, so same thing, right? With human preference is open-ended task, right? Human preference require you to have some sort of agreement between groups, right? For example, ethics. That's something that you can actually check, right? So if that's the case, then we can build some sort of classifier based on ethics, based on human value, right? So you can actually do that. Okay. So next, let's go to iterative response engineering. Okay. So this part is the most exciting part to me because it uses optimization. Okay, so it's iterative loops. So the model evaluates and refines its own output again and again and again. All right. So for iterative response engineering, the key idea here is to, instead of single post-processing pass, they're gonna attach a feedback loop. So if you see on the figure here, we have the LLM generating output. right? There's some sort of evaluation, right? There's some sort of score verified, which is done via LLMs again, or human or reward model. And then we start refining, right? And then this loop keep running, right? Until there's some sort of pass going through, okay? All right. So some methods for iterative response engineering. So we have reflection, LLM refine, mixture of agents, my evolution, and I'll work on this Memetron. Okay. The general trade-off of this is it's extremely expensive to run, right? It's risk infinite loops. It can run in infinite loops if we don't design it correctly. So it's also harder to debug and control, because when you run it in a optimization loop, you may not actually look at the debugging, right? You may not be able to. Okay, so for the first paper is very interesting. It's called reflection. So the idea of this is there's going to be a model that's going to act or output a response. Then there's going to be evaluation step. And then it's going over to the reflect step. So it's going to be verbal feedback, like refinement before, but it's also attached to a memory, right? So it's like, okay, in this step, this is my memory. So if I can rerun it again, I look at my database of memory, say, okay, in this step, I said this. So this is what I need to do next. Okay, so there's an act, reflect, and retry loop with a memory. Okay, so rich verbal feedback, but it's not just a scalar feedback. The memory persists across attempts, right? Because we also have a memory here. And reflection quality depend on the model capacity, unfortunately, right? So if you have a model that is very poor, then of course it's not gonna do well in reflection. Sure. Okay, example. Maybe the first there's going to be some multi-hop reasoning requiring chaining two facts, right? The first attempt, it may say that the answer is Paris, right? It's the wrong thing because only use the first hop. It doesn't combine the two facts, right? With reflection, you know that okay, this is wrong because my verifier or my reward model saying that okay, this is wrong. So then I go into reflect, right? I only look at the first hop, right? So I need to chain both facts together in order to get a better answer. So the attempt 2 or the second loop is gonna output the answer in London, which is correct, right? So that's how it's changing its output. Okay. Then after that, one of the I think is very interesting paper is LLM refine. So as you can see with a reflection right here, right? You can actually run it forever. There's no stopping, right? I mean, if you have a verifiable task, when you get it correct, you can stop. But for some other tasks where there's no verifiable information, you can actually run it forever, okay, without like a signal to stop. Okay. With LLM refine, we actually attach this feedback or refinement, or you can call it reflection, into a optimization called a simulated annealing, right? Optimizations algorithm. Okay, this is a local search. So basically, imagine that I have a response here, R0, right? Getting this score. Okay, I can use this scalar score to actually optimize my responses. Okay, so it can keep refining. Okay, I'll put another one, score it, and okay, and maybe it's get better, accept, and then next one is can output a answer that have lower score. It has a probability to also accept, to move out of local minima, right? So this is how you do simulated annealing, okay? So hopefully you will be able to convert to something like R star right here, right? Then you have the temperature for acceptance decrease over time, like a bandit problem. Okay. Okay, so for example, for machine translation from, for example, Vietnamese to English, there's some string, and then the output of it is going to be the translation from Vietnamese to English. So the metric X is the metric for machine translation, right? So it's got 67.5, for example. With LLM refine, is can pinpoint that problem, right? It's saying, okay, span 3 to 5, meaning that for word 3 to 5, there's something wrong with this. Maybe gifted salary should be raised salary instead of gifted salaries. So it's gonna fix that mistake, right? And get the higher metric X. Right. Next one is mixture of agents. So similar to assembling, right? Where you are outputting or you producing a lot of answers and then you combine them or synthesize. But mixture of agent, what they do is they are able to stack these layer up, right? For example, proposer 1, proposer 2, proposer 3 right here. They stacking it up, right? To proposal 4, proposal 5, 6, keep stacking it up. And then later on have an aggregator that output the final output. Okay, so the important thing with mixture of agents here is the ability to stack multiple proposals together. Okay.
These are different LLMs or?
We can use different LLMs as well as the same
Same one, then just,
Yeah, if you use the same one, then it's assembling. If you use different one, then it's mixture of agents.
How do you write for me?
You are not dividing any work. All of them doing the same type of work.
They're the same code now.
Yes, and then different one gonna output some sort of different answers. And then you're hoping that by combining or synthesizing all the answer, you get the better one. Self-consistency is about the consistency between the answer. This one is synthesizing the answer. Self-consistency is like, okay, checking how many answer got this answer, and then is it a majority, right? And then get the majority answer as the chosen answer. This one, you can combine it. It's more open-ended, right? It doesn't need to check the exact output of something to see if it's the same or not. Go ahead.
Maybe finding something that you probably call with this one. Is there any work where you also try to recognize maybe that problem? So what's that way to get a better?
That's actually a good idea. I haven't heard about that those kind of work yet. So
Yeah. I don't understand, but I'm just wondering if there's something to merge.
So the idea is like to optimize the prompt for each of the proposer, and then therefore increase the performance of mixture of agents. The system prompt, and then. All right. So concrete example for this is, again, instead of doing GPT-4 alone, Claude alone, or Mixture alone, we combine them, right? The answer of them together. in a, I would say, auto way, meaning that you can just aggregate the answers and saying, okay, please synthesize these to a better one, right? So the output here hopefully is going to be better. And then the paper show that the performance actually improved, right? So that's actually pretty good. Okay. So the yeah. That's a good idea. I'll talk about that later. I have a work on that. Memetron addresses that issue. Right. That's true.
The second thing is the time process. So it's really the same price, so you can have it done getting to the off. So there is some like then you are basically wanted to like the basic like your output. So two aspects.
Oh, thank you, Theja. Thank you. All right, so just the notice, right? Mixture of agents here is some sort of global optimizer, right? So because it's asking multiple different language models to output something and then later on converge to some answer, right? Then my evolution right here is also a global optimizer. So the main idea of this is to maintain a population of candidate responses, iteratively select, recombine, and mutate via large language model. So it's some sort of genetic or evolutionary algorithm. Okay. So first, it's going to initialize some populations. It's going to do crossover, mutation, evaluation, critique, analyze, refines, and then keep that loop going, right? So as you can see here again, the idea is that mix of agents here, they don't have a sense of objective, right? They just say, okay, please synthesize these answers together. That's it. They can stack it in multiple layers, but they don't have a sense of, their sense of optimization is synthesization, right? However, my evolution right here, what they do is they have a programmatic verifier. For example, when you're doing math, there's some problem in math that you can actually verify it via program, right? So you can use a calculator, maybe. You can also use some coding for some generalization of some math problem to do that, so that you are able to get the correct answer. Okay, and then using that correct answer is, correctness signal is correct or not, and what's wrong with it, you can actually critique and then refine. Okay, the thing with this is also have high cost, right? Because it's running over a lot of iterations and also a lot of responses in generation, right? So this is a population-based or global approach. Okay, my evolution right here, the task, for example, is a planning task. So visit 7 Asian cities. I have 5 days in in Tokyo, attend wedding on day 11. The initial solution can say that, okay, Tokyo, I do 3 days, but then it's unaligned because the task here is that Tokyo has to be 5 days, right? Not 3 days. Okay. So evaluation feedback right here can be, you plan 3 days for Tokyo, but you are required to stay 5 days in Tokyo. Okay. So critique starting to analyze, like, okay, number of days to Tokyo should be 5 instead of 3. And then the order refunds, okay, change it to 5. Okay. And next one is our work actually on iterative response optimization or engineering. So the idea of Mematron is that it treats reward guided post decoding or post generation as the discrete black box optimization over completed responses, right? So first, it's gonna assemble candidate responses, right? Global optimization, doing global optimization, score them via a black box reward model. So and then refine them using Genetron and Anetron. So Genetron is some sort of global optimization, and Anetron is local optimization. Okay, so doing global, local, global, local. Hopefully, we land to the right. Okay, so it goes beyond one shot best of n, right? It's find higher reward responses at test time, and then it's actually optimized against the reward model directly, right? Instead of have some critique in wording and then convert it into score and then do that, right? It's optimized against the reward model score directly. So I have a QR code to my paper, our paper right here. And then also have a lightning talk tomorrow on this. At Recency Ballroom ABCD, 1:15 to 3:30 tomorrow. All right. But yes, I'll go over quickly how this works, right? So for example, I already explained you about best of n, right? So basically you are generate multiple answers and then you're gonna select the best one based on a reward model, something like this, okay? So this best of n is also a global optimizer, right? Generate multiple of them, get the best one, right? So, but it's shallow, okay? Because it's only do it one time. With Mematron, what we are trying to do here is we're gonna attach the loop of, for example, best of n right here with a Mematron framework that have Genetron and Anetron here. It's gonna keep running forever to a point that you want, and then at the end, it will provide you a better responses corresponding to the better scores. Okay, so it get the responses that have better scores. Okay, so here's the framework. On the blue one, it's Genetron. So it's inspired by genetic algorithms. So you going evaluation, you're going to stop being a criterion, you do elitism, right? Population selection, right? So and then you do parent selection, you do crossover, but this time you're doing crossover using a language model, then you use doing mutation using a language model, right? The evaluation right here is going to be done by a language model, by an reward model, right? With output a scalar score, okay? And then the question is that how do we optimize against that scalar score, okay? So we actually using these two LLMs crossover operators and mutation operators to actually prompt the operators to align with the objective of the reward model. For example, if the reward model is about helpfulness, right? And then it output 3.5 score, okay? And then I use these two or these four things here to actually align with that score. So, okay, here are the answers of two agents. Can you please produce a helpful response, right? It's aligned with the objective of a reward model. Okay, and then on the right side here, we have Anetron, which is done via simulated annealing. but also using two operators, LLM as refinement operator and LLM as perturbation operator right here. Okay. The thing is that this loop is gonna keep running, right, until you get like converge your reward model converge. Okay. So here's some actual concrete examples of Memetron. So the query is that, okay, I have 5 monkeys are jumping around on a 4-poster bed while 3 chickens stand and watch. How many legs are on the floor? Okay. So an incorrect answer would be there are 0 leg on the floor with a lot of LLM answering, right? But after Memetron is the language model which previously saying 0 legs start saying there are 10 legs on the floor, 4 bed legs, and 6 chicken legs, right? And then example 2 is that, okay, if Sally is a girl, she has 3 brothers, each brothers have 2 sisters. How many sisters does Sally have? It's a mind twisting kind of questions, right? So a lot of language model will say Sally has 2 sisters, right? But it's count Sally herself, right? Reward model score gonna see that, okay, I have 0.34. But after Memetron, we getting a response with a RM score of 0.95 saying that Sally is one of the 2 sisters. So the other girl is her sister. Sally has total 1 sister. Okay, so getting the correct result. Okay, here's some quantitative results of Memetron. So for example, I have a base system here called base 16. Okay, so I just from a language model, which is Quen 3 AB, I just generate 16 responses, right? And then I use a reward model, Skywork reward V2, Llama 3.1 AB 40 million here as the reward model to optimize against. So I'll be able to see that over times, right? For base 16, I got pass of edge, meaning that out of 16 responses, if at least 1 correct, then I count it as success. Okay, I got 85%. Okay, but over Memetron generations, I get to around 95%. Okay, and then the evidence here is that the best RM here is the best reward score that I observed during each population, right? So base 16, the best one is 25. With Memetron first generation, I got to 33. And then after 5 generations, I got to 37. Okay, so this is reported as one number, but I actually calculated the confidence interval and it's significant. All right, so if you use the reward model, right, because in math, especially in AMC 12-2025 here, it's open-ended math. You don't actually have a verifiable parametric verifier. Okay, so you have to depend on a reward model. Otherwise, it's very hard to do so. Okay, so that's why this approach is perfectly fit for this. Okay, so when I get best reward model, right, we can also check best of edge. So best of the population, right, the buffer population. So if I got base 16, I got best of edge of 61.90%. Over 5 generations, I got 85.71%. And the same for self-consistency. Okay. So for instruction following is following the same signal here, right? So base 16, best RM is 16.60, but over 5 generations, I got 19.62. just for the reward model, right? Just the signal to optimize again, right? How does it translate? I use GPT-5 to actually measure the reference between each of these rows against the base 16, right? For example, reference for Mematron +1 generation, the reference over base 16 is 58%, meaning out of 100 questions, 58 of them, Mematron +1 Cheng is better than base 16, right? So over 5 generations, the number keep increasing. Okay, so that's how I use multiple signals to actually check, right? And then to compare all of the techniques. Okay, so each techniques have different ways of approaching this response optimization or response engineering problem. Okay, so some do local search, some do global search. We do both. We do global and local. Okay, however, it's not free, right? It's require a lot of compute. Okay, so you can also using some metrics to actually measure it accordingly, and then measure the improvement, right? And then the objective is going to be different across different methods. We use black box reward model. Okay, there's some summary. And lastly, we're just going to go over a hands-on on response engineering, going over static, which is the two of the popular one, best of n and self-consistency. Then we're going to go over iterative response engineering with reflection and a mixture of agents. Okay. So if you can get to the to the repo here, and then go over response engineering. Oh, yes, button down here. Okay, so please, you have this. You can go back and then run this, or after this you can run this. I'm just gonna go over the notebook, right? So that it's not getting descriptive. All right, so same thing, right? First of all, just installation, doing some installation of VOM transformer, and then make sure you have this equals 0. So the generator model here I use is Quen3 1.7b, and the reward model is Skywork reward V2 Quen3 1.7b. So I try to match the capability or the billion of parameters between the generator and reward model. Okay, so let's go over the helpers, right? It's all the same as before. So for static response engineering, inside VOLM, they already have best of n, right? Built-in best of n, but it's based on the cumulative log probability, so a log prop, right? So using that signal, internal signal, we can also do best of n. Okay, so for example, for just a single sample, just outputting a single sample, my prompt is a snail climb 3 meters up a 10-meter wall each day, but slip back 2 meters each night. How many days to reach the top? So you're working, then put the final answer in the box at the end. Okay, so for a single sample, the answer for this, after some reasoning, right, is show some working reasoning, and then at the end, it's saying, okay, 11 is my answer. But the thing is, 11 is not the actual right answer. The right answer is 8, right? So for if you do reading decoding, you we get this answer wrong. Okay, for best of n, build in. We use just use extra param is best of 32 with an attached temperature. Make it a little bit high so that every answer is going to be different from each other, right? So it's for a little bit of diversity. And then if you do best of n build in at the end, so basically it's gonna generate how many? 32 responses, and then rank the log props, and then the best one. Let me see here. Best of 32, right? So right here, let me check. Okay, the final is 8. So it's get the correct answer. Okay, so with reward model, same thing. Instead of using an internal signal, I used a reward V2 Qwen3 1.7 billion. And at the end of this, best of 32 with reward model, I hope I get an answer of 8 as well. Yeah. So the best answer here is A. So let's see, it's right. So, okay. So best candidate, number 27, score 12 point something is the highest. Therefore, there's the chosen one, and that's also the correct answer. For self-consistency, again, for self-consistency, we don't depend on a score. We depend on the agreement between responses, right? So we generate n responses, extract the final answers, do majority voting, and then return the most common. Okay, so let's do that. So I think I'm doing n equal 32 right here. So it's gonna produce 32 response, and then try to see the majority of the 32, right? Let me go down here. You can actually see the output and analyze the output as well. But when you go down, you will see this like this. So extract answers. So I think 8 is the most common here, right? So majority vote 8, right? So 8 is the correct response, right? You can also see that there are some noises, right? Like some answer 10 right here, but the majority is 8, right? Next, going over to iterative response engineering. So the goal here is the loop, right? So we need to attach an optimization loop here in. So first is reflection. So basically, I do a toy example here, generate answer, evaluate, critique the answer. After that, refine the answer, right? And then evaluate again, right? So this is a toy example of reflection. You can take a look at this and then execute. I do round equal 3. So I do 3 rounds, right? So the first answer is 8, so which already correct. So after 3 rounds, I think it is also 8, right? So, right. After 3 rounds. Okay. But yeah. Next is mixture of agents. So basically generate n independent responses, fit all of them back into the same model, and then to synthesize the final answer. For this, I use the same model, right? So it's become ensampling. But if you use multiple models, you call it mixture of agents. Can you say that again? I'm sorry. Okay. Elimination. Yeah. So try to fit the answer into the problem. To do the reflection. You mean the iterative refinement. So if you attach a memory, then yes. But if you don't have the memory, then you don't have that leaking. So the feedback is only on that response only. So there's going to be the response of the answer, response of the question. You ask what's wrong with it. Then the answer gonna say, okay, this is what's actually wrong with this. Okay, and then you refine based on that feedback. There's no elimination leaking in here, right? And one possibility of elimination leakage is you actually ask a question and then put 4 answers in, right? A, B, C, D, and then it's gonna try to actually fit, try to fit the answer and then try to figure out which one is the right one, right? But this one, we only provide the question, so there's no leakage. But it's coming from itself, right? So I don't, yeah.
So that's what you questions, the day before at the design it doesn't really take much. It's only the first page here. But you're asking the first is on, get a feedback, drop off, first page are now invalid. So you can define and get to find the correct page. Right, it says, yeah, it's not defined.
All right. All right. Thank you very much for your question. Thank you, Theja. Right. So you can define mixture of agents. For example, the number of agents I have here is 5 for 5 answers, ideally for different agents, but right now I'm using the same one, right? Sorry, right? And then there's a aggregation prompt right here. So below are 5 independent responses for the following question. Synthesize these into a single comprehensive, accurate final response. So try to resolve any errors with it, that kind of stuff. Okay. So at the end, generate 16 agent responses. And then after that, at the end, we will have the aggregation response. Okay, let's see. Yeah, the aggregation response also have 8 at the answer, which is good. Okay, so that is what I have for this tutorial. You are free to run it on your own or using the computer we have after class to run it. We are going over best of n, which is one of the easiest thing that you can do regarding to response engineering to get the better response. Okay, so you can have the built-in version, or you can have an RM version. You have a self-consistency as well, but it does require you to actually extract the final answers and then check, right? Otherwise, you have to check for similarities between answers and then get the mean of them or something like that. Okay, so and then we also going over reflection and then mixture of agents. So all 5 techniques here are training free as well, right? So so I hope that at the end of this tutorial, you have a wide range of techniques that you can use to build your or to improve or build your own language models, right? Let's go back to the key takeaway here. Sure. Okay. Okay, so training free alignment is practical, right? So before reaching to fine tuning, try training free methods first, right? Prompt engineering, guided decoding, response engineering. It's like a cherry on top, right? So because all of the language models are already optimized using training algorithms. But attaching that language model to these also still improving the performance on some tasks that they may forget to optimize, right? So this is like a cherry on top. So you try this first, and then if not working, you can try other methods. Okay. Also, they each have different trade-offs, right? Prompt engineering is manual, is zero shot, so you can just do it online. Automatic require you to do it offline. Guided decoding, direct control require logit access to or a step verifiers, right? So it's not going to be very easy to do. With response engineering, static is cheap, iterative is better, but very costly. So pick one, combine them based on your needs. Thank you very much. If you have any questions, please go ahead. And then if you want to ask us anything offline, please take a picture of our email addresses. Okay. And then there's like a tutorial survey that's required to please do a survey. Okay. And then thank you. The slides are available via our GitHub repo. So yeah, thank you very much.